Hi there, welcome to your lesson on compound interest, a very important application of geometric sequences. Let's take a look. So to begin, we'll recap two types of interest. Let's say you have €100 and two banks to choose from. In Bank A, they are offering you 6% annual interest rate on the original balance. In Bank B, they're offering you 6% annual interest compounded. So this is a key word here in banking, what compounding is. So what is compound interest? We'll take a look at that through a quick investigation. But first of all, you should know this is called simple interest, and here again we're talking about compound interest. We're going to compare these two and see exactly what is compound interest. So here's a little bit of an investigation we're going to look at. We have that 6% put into the bank with an interest rate on the original balance. So the amount that was invested in the beginning was €100. That €100 gains 6% at the end of the year because it's an annual interest rate. 6% of 100 is €6. So the interest is 6. So now the ending amount at the end of that year is €106. Now the next year you begin with the 106 that you ended with here. The interest, when we have an interest rate that's called a simple interest like this, where this 6% is applied only to the original balance, it means to the original amount, that means that every year you will continue to get in this case, €6 interest. It's always going to be 6% on the original amount. So every year, an extra 6. So if you add 6 here, you have 112. Okay, so in the third year, you begin with 112 and you gain 6 more in interest over that year. Because once again, that interest is being applied only on the original balance. You're not gaining anything from these ending amounts. So there's 6 more, 118. Next year begins with 118, you gain 6 more, and you have 124. This, if you look at the sequence, is an arithmetic sequence with a d-value of 6. It's always going up by 6, that extra 6 you gain every year. Therefore, if you're looking for an amount at some future years, let's say end of year 40, you go to year 40, you take your original 100, you add 39 jumps of 6 using the arithmetic sequence formula, and you find out you have this amount after 40 years. Okay, let's compare that to 6% annual interest compounded. So compounding is a different kind of interest, and it's a more common kind of interest. So again, we begin with €100. The interest is once again 6 because we apply 6% to that €100, and the first year was 106. Just like in the first situation, we have the same amount. Now we begin the second year with 106, but now when it comes to apply the interest in the second year, we're not giving the 6 again, because now the 6% interest is compounded. That means the 6% is applied not to the original amount, but to the amount you have at the current time. So 6% of 106 is actually 6.36. It's a little bit higher because you're gaining the interest on the 100 and you're gaining interest on the extra 6 that you see here also. So now the interest is higher. Add those two together and we have this much at the end of the second year. Now you begin the third year with that amount, and now your interest again is going to be higher because the interest is applied on this amount, not the 100, but this amount. So that is what compounding is all about. So now 6% applied to here is 674. Add that, and we have this much at the end of the year. Begin the next year, do the compounded interest again, so the interest applied to this amount, and then add it all up, and we have this. Alright, so it looks like it's growing. It's not huge because at the end of 4 years in the first situation we had 124 and now we have 126. So it's just $2.25 more. However, what if this continues for a long time? Let's take a look at what kind of sequence this is. We have these amounts here, and these amounts show us a geometric sequence. Now that there is a ratio, a common multiplier, and the common multiplier is 1.06, 1.06. We always multiply by 1.06 to get to the next amount. That being your 100% plus the extra 6% every year. So 106%, 1.06. So if we look for the amount in the 40th year, in this case we're using a geometric rule now because this is now a geometric sequence. Compounded interest amounts are always in a geometric sequence. So now we have 100 times 1.06, the ratio, and the power of 39, because there's 39 jumps of 1.06 to get to year 40. That works out to this amount. So now this is much greater than what we had in the other situation. So this shows us the power of compound interest, when you earn interest on top of interest. So to recap, we have two types of interest. Simple interest, which is interest that remains the same for each year that you have your money in the bank. It remains the same because it's always applied to the starting amount, the principal amount. And then we have interest that is paid and called compound interest. This is interest is added to the original amount, and the new value is used to calculate the interest for the next period. So we saw that happening. The new amount at the end of each year is the one that the interest is then applied to. So simple interest was that example, where we had the same amount of interest every year because it was applied to the beginning amount. Compound interest was that example, where we had the 6% applied to the ending amount at the end of each year, so the interest went up all the time. We saw that after 40 years this was 334 and this one was 970. So there again you see the power of compound interest. It grows very quickly. Here's a chart that shows that as well. Here we have the principal amount in blue, which is the amount you put into the bank. So that stays the same after year, stays the same. And this is showing 20 years. Now you look at your interest with no compounding, so simple interest, and notice that goes up in a linear way, right? Because it was a arithmetic sequence, so it goes up with a linear fashion like that. So interest, same amount gained every year. So there's a slope of the same amount gained every year. But when we look at compounding, notice it follows a geometric pattern or an exponential growth, because there's interest on top of interest on top of interest. It grows geometrically. So that is the power of compound interest. We had a formula for compound interest which looks like this. It tells us the future value can be found, the future value of our investment can be found by taking the present value and multiplying by 1 plus the rate to the power n. And all that meant here with the 100 is we have our rate, for example 6%. If you divide 6 by 100, you get 0.06, and we already know that 6% is 0.06. So this, a lot of students ignore that 100 and just remember that here if you had 6% you would just write 1.06, which means 106%. And the n here means the number of years. Don't forget that this is just another form of our geometric sequence. We just talked about that. A compound interest rate grows geometrically. So here's our geometric sequence formula, and we see that we have our beginning amount, we have the rate like we have here, and we multiply by the number of times you apply the rate. The reason we have -1 here and here it's just an n is because if you look at u2 using this formula, u2 would be u1 times r to the 1. So notice if you want to get to the second term in the sequence, it's the same as saying one jump. In other words, the end of year 1. And that makes sense because the beginning amount is the beginning of year 1, and if we go 1 year into our money making here, we're actually applying r to the 1 power, and u2 is the amount of money we have at the end of year 1, but it really means only 1 year has passed. So here's that 1 year there, and here in this formula we'd also put 1 year. Okay, let's apply the formula. So we have Petra investing 6,000 Costa Rican colones in a bank offering 4% interest compounded annually. Okay, so it's annual compounding, exactly the formula we just saw. We're going to calculate the amount she has after 8 years. So let's begin with our formula, put in everything there, and see what her future value is in 8 years. Okay, so you've tried it. We put 6,000 for the present value, we put 4% here. That 4% is applied for 8 years. Okay, that becomes this, because 4 divided by 100 is 0.04, 4%, so now we have 104%, 1.04 for 8 years. That tells us the same thing as this. Remember, I'm just going to compare it again, this formula, because I don't want you to forget that this formula is just simply a geometric sequence. If we use a geometric sequence, we would say start with 6,000, multiply by 1.04, and multiply by that amount 9 minus 1, because again, don't forget, if we're going to jump to the end of year 8, we're doing actually, that's term number 9, because that one at the beginning of year 1, basically term 0 was our first one. So we're looking for 9 terms, and that is going to give us year 8 here. Okay, so at the end of year 8 here is the same as this. Notice that our geometric sequence and this formula are the same thing. And the answer to that is this number here. So hopefully that's what you got. Now let's take this question a step further. It says, Petra then withdraws all her money, so she took it out of that first account, places in another bank that offers 4% interest per annum compounded monthly. Now it's compounded monthly, so this is a little different. What happens when the compounding is no longer done every year, but done different intervals? Let's check. And the question is, how much does she have after 5 years? So let's take a look at this together. So we have our future value formula. We will put in the present value, which is the amount she took out from the first bank, which is the amount we just calculated a moment ago. So she took this amount up and put in this new bank as her present value. Then she has a rate of 4% again. So we put 1 plus 0.04 from that. And then we put 5 years here. But this is not right. This will not give us what we need because it says that it's compounded monthly. This would assume that she's paid every year. And there's 5 years here. But if it's compounded monthly, what the bank does is it takes its annual interest rate, which is 4%, and it divides that annual interest rate by the number of compounds. So here it says compounded monthly, so they take their annual interest rate of 4% and they divide it by 12. So they kind of divide the interest into 12 parts because they're going to pay you every month. They're not going to pay you 4% every month. That would be too much. So they're just going to pay you that 4% annual rate divided by 12, and they'll pay you a little piece of it every month. And then over here, we add the 12 as well, because now you're not being paid just 5 times, you're being paid every month. So you're being paid 5 years times 12 months. You're going to be paid 60 times. That means once every month for 5 years. So the 12 appears here and here. That's how compounding works. So compounding monthly, we saw that appear. So that works out to this big decimal value here. If you calculate that, it would be that. And now let's see if you can get an answer from that. How much will she have after 5 years in this second account? Alright, calculate it and you get this amount here. So the key thing here again was this compounding monthly, and it included adding this extra bit here. So what that means is we have our formula for compounding, which was our basic formula here. And now that has been converted into a more detailed formula, which looks the same, except for I see there's a k there and a k there. And that k is what we just saw happening. It's the number, or k is the number of compounds per year. So we divide the rate by however many times we're compounding every year. And when we saw monthly, we made that a 12. If it said compounding every day, you could put 365 there because there's 365 days in a year. Or if it was compounded twice a year, you would put a 2 there because the rate is divided in half. So that's how that formula works. Let's try it out. So here's another problem, just like the one we just saw. Try A first. Find out the amount of money this person has after 5 years in its annual compounding in that situation. Okay, check your work for A. Annual compounding, and there's the amount here. Okay, now try B. And B, they take that money, just like we did in the last question, they take it out of that account, they put it in a different account, and it's compounded monthly. Try B. Okay, so in B, that amount that came from there goes into this one now, and now it's compounded monthly, so we see the 12 there and 12 there. There's 36 payments in total now, and that rate is divided by 12, and we get this amount. So hopefully you got that to work out as well. Okay, let's try another one. Try this one here. How much will Alexis have after 6 years in this bank compounded quarterly? Quarterly means compounded 4 times in a year. Okay, check your work here. We use the formula. Notice we have a 4 here now because the rate has to be divided by 4, and then we also pay out 4 extra times. So now it's, instead of 6 payments for 6 years, it's 24 payments in total. There's the total amount. Now try B. Okay, we're trying to see when this payment will double, so we have the 80,000, and here's a future value that has been doubled. Remember, when we do this here, we have an equation with a variable here. We can't solve that. We can solve it on our calculator by graphing. So we enter this as y1, we enter this as y2. We have 2 equations, we graph them, and we see when this curve intersects this horizontal line. And that will tell us when these 2 amounts are equal. That should give you an end value of 23, telling you it will take about 23 years. Make sure you know how to do this on your calculator. We've done this a bunch of times now, so just try this again. Graph them both and find the intersection point. Great job. Let's try one more. Check your work for this one. and it looks like Swedbank is better.